All right, everybody. Here it is, the meat and potatoes of this lesson, the limits of rational functions. So here, what is a rational function? You have to think of it as like a polynomial over a polynomial. So here, it's saying as the limit as x approaches a of some polynomial over a polynomial means that all you need to do is plug in the a value, granted that whatever the denominator is, that it's not equal to 0. That's how you read this. But let's do this. Here, notice that this rational function we've seen a lot. So for this one, notice that how does the top factor? It's x minus 4, x minus 2, and what's on the bottom? It's just x plus 3, x minus 2, right? And here, x cannot be minus 3 and x cannot be 2. So notice that if I'm trying to find the limit as x approaches 5, x equals 5 does not make the denominator equal to 0. So all we need to do is just plug it in. And that's what this definition is saying, that you're allowed to plug in the limit, granted that the denominator does not become 0. So to solve the limit for this, all you need to do is just do 5 squared minus 6 times 5 plus 8 divided by 5 squared plus 5 minus 6. Whatever this answer is the limit as x approaches 5. Okay, and I'm sure we could all do this by ourselves. But it gets very spicy, or it's when we have to find the limits of these values at -3 and at 2. So let's take a look at it and see what happens. Here, notice that for this, and here we have the same polynomial function, right? We're just trying to experiment what this looks like. Here, this is where it gets a little tricky. We know that if I want to find the limit as x approaches -3 from the left and -3 from the right, we know that, remember, when we factored this, there has to be some vertical asymptote at x equals, I'm sorry, this should be a -3, because the x plus 3 did not cancel out. So here at x equals -3, you have a vertical asymptote, right? You have a discontinuity there, and this is what we've been talking about in the last lesson. So there's an infinite discontinuity at x equals -3. So the idea is, if you know there's an infinite discontinuity at as x is going to -3 from the left and x is going to -3 from the right, like here, this is -3, you know that there's some asymptote. So you know that the graph has to go from the right side, it has to go to either positive infinity or negative infinity. And the same idea going from the left, it has to go to positive infinity or negative infinity. But how do you determine which infinity it goes to as it approaches -3? And the idea is, all we need to do is just plug in a value to the left of -3 and to the right of -3. And notice that, if I have the number line, right? If this is -3, what's a number left of -3? What's a number smaller than -3? It's like -3.01. And -2.99 is bigger. So this is coming from the right. So this is from the right over here, from the right. And this is from the left, right? So if we plug in these values into our original function over here, it'll tell us whether the value is positive or negative. So let's just take a look over here. So what Mr. G did to save some time is let's see if we can see this. Notice that I plugged in this graph into the calculator. So then how do I check the value of -3.01? Don't you remember our command? We go to vars, yvars, function, y1, and all I'm going to do is plug in this -3.01, -3.01. And here, if I get a positive value, it goes to positive infinity. If I get a negative value, it goes to negative infinity. So let's see. I have a positive value over here at 701. So then this has to go to positive infinity. And let's try it for the -2.99. Notice that if I do vars, vars, yvars function, y1, and let's put in -2.99. Notice that you get a negative value of -699. So this is going to negative infinity. And let's just look at the graph to make sure that this is okay. You see, like if I hit graph, notice that at -3, this is -1, -2, -3. Notice that from the left, it does go to positive infinity, right? Didn't we just say that? From the left, it does go, oh, sorry. You see, from the left, it does go to positive infinity. And notice that from the right, it does go to negative infinity. So this little idea of plugging in the number works. So notice that if this is going to positive infinity, and this is going to negative infinity, what about, you see, from the left, from the right, does the limit actually, my bad, does the limit actually exist? And here it does not exist. Okay? Now, let's go do the next part. Here, what about at x equals 2? Remember, x equals 2 does not work either. So the idea is, here, if we look at our graph at x equals 2, it has a removable discontinuity. So the limit exists. All we need to do to find where this limit goes, if you actually look at the graph, oops, sorry, the glare, okay, that's good. At x equals 2, it goes to some y value. So all we need to do is just factor, simplify, and plug in our value of x. So if we factor this, this is x minus 4, x minus 2, and this is x minus 3, I'm sorry, x plus 3, x minus 2. And notice that all we need to do is cancel these x minus 2's and then just plug in the value of 2. So I have x minus 4 over x plus 3. And now this just becomes 2 minus 4 over 2 plus 3. And this becomes negative 2 over 5. So the limit as x approaches 2 of this function, it approaches negative 2 over 5. Okay? And we know that the limit for the left and for the right is also the same because the limit exists. Okay? Here, this is the summary we have. If the limit as f of x as x approaches a, if x equals a is not a discontinuity, then just plug it in. And which example am I talking about? It was the first one. Here, this x equals 5, this as x approaches 5 doesn't make the denominator 0. So you're allowed to just plug it in. For here, if the limit of f of x as x approaches a, if x equals a is an infinite discontinuity, then you need to play the game of plugging in a number to the left and to the right to see which infinity it goes to. For the removable discontinuity, which was this example here, we know that this is a removable discontinuity because these x minus 2's cancel, right? And that was the property of removable discontinuity. All you need to do is factor, simplify, and plug in the value of x equals a. Okay, I hope this helped. I'll see you.